Yesterday's dinner was super good, but I think I'm not going to eat too much today for lunch. But thanks for the very lovely event to share. Well, speaking about yesterday, this was the last slide I finished with yesterday. So this nicely summarizes what we have been doing so far. We introduced a certain framework, data informativity framework, and we discussed certain problems, whether analysis or design problems within this framework, first with exact data and with noisy data. Well, those in red are problems we studied during the lectures, and this blue was in the tutorial session. In all these problems, we were interested in finding conditions on data so that the data are informative for the given problem. And if the data are informative for the given problem, either we can say the system has a certain property, although we don't know the system, or we can design a certain controller which achieves a certain control objective for the unknown system. Okay? These are all very nice results, I would say, but their usefulness is limited. It is up to the informativity of the data one has. If the data are informative for, let's say, stabilization by state feedback, so it satisfies certain conditions, then I can find a stabilizing state feedback. But if the data are not informative, then we are lost. We don't know what to do. Well, we can maybe collect more data, try it again. But it would be nice to complete the picture by generating informative data for the problem at the hand. So the ultimate goal is for any of these problems, I want to devise an experiment, an online experiment, to generate informative data. By an experiment, what I mean is I want to apply one input, see the output or whatever I am measuring, and now I have more information about the system. By looking at the data I have, I want to determine the next input, and I do this iteratively and guarantee that at a certain point I'm going to have informative data. This is a much more difficult problem than finding conditions on the data for informativity. And what we also know from the analysis of informativity that conditions change, which means that these experiments are going to be also for a given problem. Okay? But that would be the ultimate goal. If I have experiments for all the problems I have studied already, then it is going to be a complete theory which is parallel to model-based theory. Because in model-based theory, if we have the mathematical model, we can always design a stabilizing controller if the system is stabilizable. Okay? So that we don't have yet, but we started already thinking about it and working on it for some time. And the first try was, let's forget about all these different problems and focus on system identification. Can I design an online experiment for system identification? So today's topic is an online experiment for system identification. But to be able to come up with an online experiment for system identification, first we need to find out data informativity conditions for system identification. Okay. And so this is what I'm going to do today. And then Henk is going to present the online experiment. All right. So what about good news, bad news? Good news, there will be no proofs. Slightly bad news that to follow everything to a certain extent, one needs to remember several definitions I'm going to make along the presentation. And they are going to be on the slide, but I'm going to write some of them on the board, so hopefully we will be on the same page. But again, you please don't hesitate to interrupt me if you have any questions. By the way, maybe I can tell the story behind this research a bit later. Okay. Now, I'm going to use pretty much a standard notation, apart maybe from these 3 points. Well, the integer intervals we have seen already in the first day. I'm going to write ij interval, which denotes the ordered set of integers from I to j if I is less than or equal to j, and ij interval is empty if I is greater than j. Okay. For a given set of vectors, f0, f1, fk, all with the same dimension, I'm going to denote this matrix, which has these columns as f0, f1, fk, by this notation f0k. And I'm going to also freely use sometimes fijk. So it starts from fi and at fj. Another thing is, I will allow matrices to be void matrices, so they may have 0 rows or columns, which means that they disappear from the context then. This helps me to write partitioned matrices in a compact way. If there's a matrix with 0 rows in a certain formula, or with n rows, let's say, and if n is 0, it disappears. Okay? Now, so there is one more thing that maybe the only thing that is not maybe too standard. It is the leg of an input state output system. So if I have an input state output system of this form, where M denotes the number of inputs and the number of states, P is the number of outputs, M and P are at least 1, so I have some inputs and outputs, but N can be even 0. So if N is 0, basically the first line disappears, X disappears from here. I am looking at a memoryless system. Yt is equal to d times ut. It's a static gain. Okay? And throughout the talk, I will work with fixed M and P. M and P are fixed. Because I'm going to start with some input-output data, so I know the number of inputs and outputs. But anyway, if I have such a input state output system, I can define the kth observability matrix as omega k, as we have done earlier already. I don't, by the way, assume at this point anything about the system, like observable or unobservable. It's just any A, B, C, D. Then the smallest integer L such that rank omega L and rank omega L plus 1 is equal, are equal, is going to be called the leg, and denoted by LCA because it's a property of C and A only. So if I look at these matrices, of course, if I increase K, basically I add new rows, which means that the rank cannot decrease. As K increases, the rank increases, right? But the rank can be at most N. Therefore, at certain point, rank of omega K and rank of omega K plus 1 is going to be the same, are going to be the same. And the smallest of such K's is the leg. Okay? If the system happens to be observable, of course, this is going to happen, this equality is going to happen only if they are equal to both N. Because at certain point, this rank is going to be N if the system is observable. Is this point clear? Yes. Sorry?
Why only N is greater than
Because I allowed N to be 0. If N is 0, then L is 0. If I allow void matrices, because if, let's see, if there are no states, basically this is a void matrix, right? This is a, let me see, this has 0 columns. Therefore, already at 0, omega 0 and omega 1 are going to have the same rank, and it's going to be 0. Okay? So now, and naturally, because of Cayley-Hamilton theorem, if I look at rank of omega n and rank of omega n plus 1, they are going to be the same because of Cayley-Hamilton theorem. Because Cayley-Hamilton theorem says nth power of n is a linear combination of powers less than n, right? Therefore, this leg is going to be always between 0 and n. Yes? If the system is observable, yes. But I didn't assume observability. But if the system is observable, indeed it is the observability index. Is it defined? I'm not sure if it is defined for unobservable systems. Yeah, okay. Then it is observability index indeed, yes. Yes. I mean, since I don't start with a physical system, it is difficult to give a physical meaning, but it is, in a way, number of delays you need to relate outputs and inputs. Okay. Now, the problem. This is system identification problem. So here is the background. I am not a system identification person. I never studied system identification myself, but Hank was a PhD student doing actually something not related to data-driven. It was about networks and topology reconstruction of networks and so on. And one day in my room, I have a sizable chalkboard. He was explaining subspace identification to me. Fundamental lemma is used and so on. And then we started to I immediately asked myself and also later to Hank, what are the necessary and sufficient conditions? Because fundamental lemma gives some sufficient condition, right? But what are the necessary and sufficient conditions? It turned out that nobody studied it for some reason. And if you remember fundamental lemma, it's about input Hankel matrix at certain depth, and it needs to be full row rank. So it is clear that necessary and sufficient condition is going to be a rank condition on a certain Hankel matrix of inputs and outputs, right? We discussed, and at certain point we stopped because Henk had a better intuition, and he said it may happen that it depends on the system because it was a tough problem. And then we stopped. But later on, as a hobby project, I started to work on it. Okay? But the very first thing I struggled with was the formulation of system identification. What do we mean by system identification? I think it was the first day, and there were many questions about this upper bound on the state space dimension. Whether we can estimate it, why do we need it, right? Without an upper bound, of course I'm going to talk about exact data, no noise and so on, so it's a very theoretical result in nature. But without an upper bound, it is simply impossible to identify a system. If we do not know an upper bound on the state space dimension, it is simply impossible. And I can convince you by giving an example why it is impossible. Imagine that I have this data. Okay? So, capital T samples, right? Then I take this linear system for K as a parameter, Okay? Now, this system does not restrict the values of output up until this time instant, t plus k. Because at t plus k, output is going to be equal to u of 0. But up until capital T plus k, it does not restrict the values of output, right? Which means that this data is going to be generated by this system. And I can take k to be as large as I want. And if I write down a state space system for this input-output representation, then for large k, I'm going to have very large state space dimension. But if I don't have a bound on the state space dimension of the true system I want to identify, I cannot distinguish, say, this system with k to be 1 and k to be 1 million. They both generate the data. I can have some hope if I have an upper bound. So the upper bound is a necessary prior knowledge. Without upper bound, we cannot do it. But you see, even when we say system identification, we have we have an idea about what it is, right? We want to identify the system. But if you want to formally define it, you need to think a bit. It is not immediate. The first thing I'm going to do is to formally define what I mean by system identification. Because if I don't have a definition, of course, I cannot work with it. So what I mean is the following. I have a true system given by A true, B true, C true, D true matrices. But all these matrices are unknown. Even the size, even the number of states is unknown, which I'm going to denote by N true. And the leg of the true system is unknown, which I denote by L true. So there is an unknown system with these true parameters and matrices. What I assume, though, that A true, B true, C true, triple is minimal. So A true, B true, controllable, C true, A true, observable. Okay? So these are the dimensions of these matrices. And I also allow the system to be a memoryless system. Maybe it's just a static game. So N true can be 0. Okay? So I don't assume anything about the system apart from this minimality, which I'm going to come back here later on. And so we have an unknown true system. And we want to identify it from given data. So this set of data is given, input-output data. There is at least one sample, so t is greater than or equal to 1. And it is generated by the true system. What does that mean? It means that there is a state matrix, x0 capital T, and these relations are satisfied. Okay? So data is given. Data are given, sorry. I didn't study Latin. In Turkey, we don't study Latin. Nowadays, they study Arabic, I think. Or they are almost there. But in the Netherlands, high school students study Latin, and Henk corrects me all the time. Data is plural. The singular form is datum. So when I say data is, then he gets angry with me. So therefore, I have to say are all the time. So data are generated by the true system. And then what? Let's think about now, what do we need more? I already mentioned that I need an upper bound on the state space dimension. Otherwise, it is impossible. But there are other pieces of information I need to know, like observability, for instance. If the system is not observable, there is no way that I can say anything about the unobservable part by looking at this input-output data. Because unobservable part I don't see in the output. It can be just anything. Therefore, we need to assume observability to begin with. But basically, you see, observability is a property of the system. Upper bound on the state space dimension is another property. So system, whether we can identify the system or not, does not depend only on the data, but also some prior knowledge we have about the system. Like if it is not observable, we cannot do anything. If we don't know an upper bound, it's a prior knowledge. We need to know in advance. It is not something we can estimate, we can find out somehow from the data. It needs to be given together with the data. Otherwise, it is impossible. But then the question is, how to formalize prior knowledge. So I opt to come up with an abstract definition so that if I have different types of prior knowledge for different problems, I can still embed all sorts of prior knowledge into that definition. I want to come up with a general definition of system identification up to given prior knowledge. And whatever prior knowledge you have, it applies, this definition applies to, in that context. Is this clear? It's going to be even more clear when I start defining things more precisely. So there are two ingredients at this point I want to talk about. One type is at the level of systems, nothing to do with data. Well, I will define system classes first so that I can easily talk about different types of systems. So a system of this form, I'm going to identify by this matrix, A, B, C, D matrix. And now there is one-to-one correspondence between input, state, outputs, systems of this form and matrices of these sizes. And again, P and M are in bold because they are fixed. But N is not fixed. Okay? So all possible input, state, output systems with M inputs, P outputs, M and P are fixed, is going to be denoted by calligraphic S. So this is all possible systems of this form. Well, matrices actually, but they correspond to systems. I identify systems by matrices. Okay? Among these systems, there are specific ones I am interested in. For instance, observable ones. Then I'm going to use this notation, calligraphic O. Something in calligraphic O means that it's an observable system. Again, among all these systems, there are minimal ones. So they are observable already, and on top of it, AB is controllable, so they are minimal systems. Already I made the assumption that the true system belongs to calligraphic M. It is observable and controllable. Well, again, among all these systems, there are systems with N states. Those are going to be denoted by this notation, systems with N states. Among systems with N states, there are systems with leg L. And this is going to be the notation. L comes first, and then comes N. Okay? So I guess I don't need to write these because they are kind of self-evident. What we need to remember maybe is that if I have only one variable, then it is the state space dimension. If I have two, the first one is leg, the second one is state space dimension. Okay? And these are systems, and they have nothing to do with data we started with. Now, yes? Now I'm going to, yes, of course, yeah. I'm going to tell something more about the story behind this result. At a certain point, we had to make a decision whether we should write it for state space or in a behavioral framework like autoregressive models. It felt like autoregressive is going to be, at least for some reasons, easier. For some other reasons, it looked, it's not going to be so easy to formulate, so we doubted quite a bit. But they are equally likely. I mean, it's just a matter of preference. And at a certain point, we decided to write for state space systems because then it is more accessible for a larger audience. But now we are writing another paper, and it starts with autoregressive, and it becomes even much easier. And I will explain later what I mean by that. Even the definition takes so long here. There it is much easier, much more natural. But yeah, we made this choice already. But it is a very legitimate question. And let's discuss it a little bit more when I finish the definition. But first, we have system classes, nothing to do with data. And now, I define systems which are related to data. In the following sense, I'm going to say that a system explains the data or consistent with the data, as we have said earlier, if there is some state satisfying these relations. So if these relations are satisfied for some x, it means that ABCD system can generate the given data. Okay? And there could be many of these systems, of course. So I'm going to define all systems that explain the data, that explains the data as calligraphic E, explaining systems. And I do the same. Those with n states, I denote by En. Those with leg L and n states, I denote by this notation, calligraphic E, Ln. We have S, Sn, Sln, and E, En, Eln. S means that it's just a system. E means that it's a system that explains the data. Yes, yes. But we use this in double. We couldn't decide which one is better, actually. So you can read explains as is consistent. Explaining system means data consistent system. And so now we are getting close to the definition, because what do I want? I want somehow this set of explaining systems small enough so that I can say, okay, this is the system I started with. But the problem, of course, well, since the data are generated by the true system, that the true system is an explaining system with leg L true, state space dimension n true. And the other inclusions are obvious. Well, obviously we cannot, it is impossible to identify A true, B true, C true, D true, right? We can only hope for finding A, B, C, D that is similar to the true quadruple. Because we measure only the input and the state. If I make a similarity transformation on the true system, it's going to generate the same data, right? Therefore, I cannot distinguish between A true, B true, C true, D true, and any other system similar to true system. For that, I need to introduce, how much time do I have before the break? Where is Himanshu? I have 45 minutes. Okay.
I have one more question.
Yes.
So, can you go back to the previous SN, which is the training system with N states?
S is just systems with n states. En is explaining systems with n states.
SN.
Mm-hmm.
Once you fix N and if A, B, C, D are known, is L not fixed?
That's a good question. I think what you want to say is or ask is if I have an explaining system with n states, let's say 2 with n states, can it be that they have different leg? They can. They can. No? Well, unfortunately, they can. But let me come to that point again, because there is another point where this is going to be relevant to discuss. So I'm going to call 2 systems with n states isomorphic if they're similar, which means that D's are the same, and A's, B's, and C's are related by this similarity transformation S. Then they would have the same input-output behavior, same transfer matrix, same Markov parameters. From input-output point of view, they are the same. Okay? And if I have a set of systems, say S prime, with all with n states, I'm going to say that this set S prime has the isomorphism property if all systems in S prime are isomorphic to each other. Okay. Now, I am ready to define what I mean by system identification. I need just one more thing. I talked about prior knowledge. I need to capture, in an abstract way, what I mean by prior knowledge. It is simply captured by a subset of all systems, which I call SPK for prior knowledge. It's just any subset of all systems which contains the true system. Okay? Whatever you know about the true system can be captured by this set SPK. I may know, for instance, A is stable, right? That would correspond to a subset. I may know also it's minimal, for instance, like I assumed. I can capture everything I know by a subset of all systems. In such a way that a true system is one of them. Okay? Now I am ready to define informativity for system identification. I'm going to call the data, input-output data, informative for system identification within the prior knowledge set if 2 properties are satisfied, 2 conditions are satisfied. One, and let's try to read these mathematical formulas. This says all explaining systems which satisfy the prior knowledge must have n true states. Because the right-hand side is a subset of the left-hand side. This is the set of all explaining systems. This is the set of all explaining systems with n true states. Equality is possible only if all systems on the left have the same state space dimension and it is n true. So basically the first condition says that the data determine the state space dimension. And indeed, if the data do not determine the state space dimension, if there are two explaining systems which have different state space dimensions, then I cannot identify the system because I cannot say which one is the true system. To begin with, the data need to determine the state space dimension. And secondly, all systems, all explaining systems with n true states must have the isomorphism property. They must be all isomorphic because if I have two systems with n true states that are not isomorphic, then again I cannot say which one is the true system. But if these two conditions are satisfied, then I can identify the system. There is, up to state space transformation, there is a unique system within SPK that generates the data. This is a kind of abstract definition, depending on what kind of prior knowledge you know. You have a certain, if you specify SPK, I mean, you have, for different SPK, you have different, conditions. Is this clear? I did assume that the true system is minimal, but here I didn't assume anything about the system. Right? So this is the data. But I'm going to choose SPK as a subset of minimal systems in this talk. You see, I can choose, for instance, SPK equal to S. Not a subset, but equal. Then it is not possible.
Yes.
Yeah. Sure. Sure. I can take pretty much everything here in SPK, but of course it may be impossible or it may be very hard to characterize this, but SPK captures whatever we know about the system. At the moment, I keep it open, whatever. But now I'm going to specify which type of prior knowledge I'm going to work with in the rest of the talk. But one point about autoregressive models, this definition becomes super simple if we start with behaviors, for instance. It's just one line that first you define unfalsified models, and then it should be singleton set of unfalsified models. Mm-hmm. Yeah, true. Yeah, well, you can, but you cannot identify anyway. Yeah, you cannot identify anyway. But we have a general definition. I didn't specify what SPK I'm going to work with. And here I specify SPK. So I'm going to assume that I know upper bounds on the true leg, which is given by capital L, and true state space dimension, which is given by capital N. So these are a priori known. They need to be, at least one of them Needs to be known, otherwise it is impossible. Yes.
Capital M. So,
Capital N.
yeah. So, hierarchical kind of means, for instance, let's say, but I can represent that system of order P, O, I. All these systems, and those systems are going
Yes, but this one is going to be both minimal, both observable and minimal if I write a state space. So without knowing, is this where you want to go? Without knowing N, we estimate it or something?
I'm not saying without knowing, I'm just saying that I can choose any.
Okay.
So let's say the original system order is minimal order is 2. I can reprint with order 3, 4.
Sure.
N could be then 3, 1, then 2, then 4, 5. But all these are maybe part of not minimal order.
But that is the issue. How do you know? Huh? How do you know that your system is two-dimensional? How do you know that there is no minimal three-dimensional system that explains the data? That is the crux of the. I mean, huh? That is the issue. So there is no way to escape from an upper bound. Either L or either capital L or capital N needs to be known. Otherwise, it is impossible. I can write examples of this sort. One of them at least needs to be known. So I assume these bounds are given, and then I look at all systems that obey these upper bounds. All systems whose legs are less than capital L, state space dimensions are less than capital N, and I collect them in this set as Ln. These are systems whose legs are less than capital L, whose state space dimensions are less than capital N. Okay? So what I know is that the true system belongs to this SLN set. And also I know that the true system is minimal. I made an assumption already. So therefore I take this prior knowledge set. What I know about the set is A, it is minimal, and B, its leg is less than capital L, its state space dimension is less than capital N. This is what I know about the system. But it may happen that you know more. Then you can embed it here. You can take another SPK, maybe a smaller SPK. But I'm going to work with this one, which is the, in a way, most common one. Any questions? And now we have a formal definition of informativity. N-true should be determined by the data, and all explaining systems which have N-true states must be isomorphic to each other. Then and only then I can say, okay, this is the true system. Okay. Now, let's look at fundamental lemma and what it says in the language we developed, in the vocabulary we developed so far. It says that if the number of samples is at least this number, given by the upper bounds L and N and the number of inputs, and on top of it, the input is persistently exciting of order NL plus 1, which means that this Hankel matrix has full row rank. Then the data are informative for system identification within the class we are interested in. This is what it says. So it is a sufficient condition for system identification. Let's make some observations. To begin with, it's a sufficient condition, but not a necessary condition. I don't have any example, but I can easily cook up examples of that sort. And one should also feel that it cannot be a necessary condition because this condition is only on the input of the system, not on the output of the system. How is it possible that necessary and sufficient condition is going to be on the input only? And my goal is to come up with necessary and sufficient conditions for system identification. Now, the first thing I ask myself is, I define L-min and N-min. L-min is the minimum lag required to explain the system. There are explaining systems. Among all explaining systems, L-min is the possible smallest lag. And N-min is the possible smallest state space dimension. Okay? So I want to find out first L-min and N-min in terms of the data I started with. But this doesn't look easy, actually. I don't know how to even start. How can I characterize L-min and N-min in terms of data? Forget about L-min and L-min. If I go back a little to the definition of explaining systems, and I want to write it on the board, I say A, B, C, D explains the data if there exists x0t such that x1t y 0t minus 1 is equal to A, B, C, D. X0t minus 1 U 0t minus 1. Let's forget about characterizing these integers, but let's focus on finding just one explaining system. I don't care whether it has the minimum lag or minimum state space dimension, just one. Well, I did came up with one in a generic way, right? But this is going to lead a very big state space dimension. At least if I look at the definition, from the definition, what I see is that there are the only knowns are the input and the output. So I do not know A, B, C, D. I do not know X. I do not know the size of X even, the number of rows. It's not a trivial thing to come up with a sensible explaining system even. And one needs to do something else. It's not direct. Okay? But in particular, I'm interested in these numbers. And I ask myself, can I characterize them? Can I obtain them from the data? Well, it seems it is possible. One defines, for that we need to define two Hankel matrices. The first one is something we have seen. HK is is HK. Is it Y first? Yes. HK Y0 T minus 1 and HK U0 T minus 1. And this is something we worked with before, but the order was different. First, inputs and outputs we were writing. In this case, I write outputs first and then inputs. But GK is something we didn't work with so far, and the difference between HK and GK is that this row containing the last outputs is deleted from HK. GK is a submatrix of HK, and it's obtained by deleting this last row of outputs. So if I write it in the earlier Hankel notation, GK is going to be, here I have HK U0 T minus 1, and here I have HK minus 1 Y 0 T minus 2. Okay? Well, since I have the data, I can form these matrices for H starting from 1, 2, 3, 4, up to capital T. So I can easily form these Hankel matrices. Agree? Well, small k starts from 1 and runs up until capital T. Then at capital T, this becomes a column vector. Y0 up to Yt minus 1, U0 up to Ut minus 1. So k runs between 1 and capital T. And I consider all of them. Now, this is a definition for the kth. Okay? So now I make an assumption on the data, namely that the input data is not identically 0. I mean, this is a very reasonable assumption, because if it is identically 0, then there is no way that we can identify the system, right? B matrix can be arbitrary, D also. Well, we will immediately see why I make an assumption of this sort. I mean, it's not essential, but it just makes our lives easier. And it is because of the definition of these integers. Now I define integers delta k. So delta 0 is equal to p, the number of outputs. Okay? Delta 1 is the rank difference between H1 and G1. If you look at H1 is going to be Y full, U full here, no shifts. G is going to be only U, because Y part is dropped. Delta 2 is the rank difference between H2 and G2, and up until K to be T. Now, one can see that these P is going to be delta 0. Delta 0 is going to be greater than or equal to delta 1. And these are non-increasing integers. Okay? Let's look at the last one, delta t. Well, ht is going to be, I take t here, which means that it is going to be a column vector. It is going to be from y0 to yt minus 1, and then the same for u. If I look at gt, this is going to be y0 up to yt minus 2, because I'm going to delete the last block of y's, and u0 up to ut minus 1. Okay? Because of the assumption, this part of the vector is not 0, which means that rank of ht is going to be 1. It cannot be 0, because this is not 0. It cannot be 2, because it has one column only, so it must be 1. By the same logic, this part is not 0, so rank of gt is going to be also 1. Therefore, delta t is going to be 0. Rank ht minus rank gt. Right? So we are looking at integers that are non-increasing, and the last one is 0. Okay? Now I define q to be the smallest integer k, such that delta k plus 1 is 0. Because this guy 0 means that there might be some other guys that are 0. I find the smallest k such that delta k plus 1 is 0. That's a well-defined integer which I can compute from the data. First, I can form H and G matrices. Then I look at these rank differences and find out Q. Agree? It's just based on the data I can find out. How much time we have before break? 3 minutes. 15. I was going to have a heart attack, Himanshu. And this Q is going to be naturally between 0 and t minus 1 because k is between 0 and t minus 1. And you agree, right? If somebody enters this room with a bunch of data, I can find H1, G1, H2, G2, delta 1, delta 2, and so on, and determine what Q is. Now, there are some inequalities I can prove on the basis of this number Q. If I have an explaining system with leg L, state space dimension n, then the following statements hold. If the number of samples t is greater than or equal to L plus 1, then L needs to be greater than or equal to Q. If L is greater than or equal to Q, then n minus the sum of deltas from 1 to Q has to be greater than or equal to L minus Q. Now, at this stage, of course, you should ask, like, okay, where does this go? Because you may think like it is the TV series, The Lost. Have you seen it? I haven't seen it. It was on BBC. People were crazy about it. But, you know, it was getting more and more eclectic. And there were new characters, and then everybody hoped for a marvelous final. But of course, they couldn't wrap it up, because the story spread around. Everybody I know was very disappointed. But don't worry, we are going to wrap it up soon. The issue here is, from the data, I can figure out these integers, delta integers, and this integer q. And they have such, they lead to such inequalities, which we are going to use soon. Now, I'm going to say that X is a state for the data if there exists A, B, C, D satisfying this relation or this relation. And I was talking about finding one explaining system. If you can find a state, then finding an explaining system is very easy. Because if I have the state here, then this is nothing but a linear equation in ABCD. So the issue is creating a state for the data. Once you have the state, then you can solve ABCD from these linear equations. Well, one can also easily characterize what it means to be state. X is a state if the row space of this matrix is included in the row space of this matrix. Because then and only then these linear equations are solvable. But the question is like, now, given data, how can I create a state? This is a non-trivial question, but it turns out that, here is the nice thing about the delta numbers, there is always an explaining system with state space dimension equals to sum of the deltas. And it turns out that all such systems have the same leg, and that is Q. These are seriously non-trivial statements. Okay? And the proof is based on a certain state construction. To prove the statement, we construct a state from data which satisfies this relation. Okay? But when I started the discussion, I said I want to characterize L min and min, and I introduce delta integers, I introduce Q. There are these inequalities, and now I know something about explaining systems. There is an explaining system with that many states, for instance. What about L min and N min? Okay. This is the definition of Q. These are the inequalities we have. And then we know there is an explaining system with that many states and leg Q. And here is the answer to the question I started with. L min turns out to be equal to Q. N min turns out to be exactly this sum. And all explaining systems with N min state has the same leg, which is L min, and they are all observable. Okay? Now, I know what L min and N min are. And how do I prove this statement? Well, I would argue in the following way. This is here I show the existence of a system with leg Q and this many states. this Q is going to be greater than or equal to L min. And if you use these inequalities, then you see that Q and L min need to be the same. It follows from the Green theorem, basically. Very simple inequalities on integers you write down. But now I know how to characterize L min and N min, and also the proof of Blue theorem is constructive, so I can even come up with A, B, C, D, which has leg L min and that has N min states. Okay? Why is it going to be observable? And the answer is very simple. If it is not observable, I can cut out the unobservable part, but then N min would drop. But N min is the possible smallest one, therefore, it needs to be observable. Okay? In particular now, if we look at the Green theorem, Q is L min. This sum is N min. So it says that every explaining system with leg L and state space dimension N satisfies this inequality. The leg of an explaining system cannot exceed its state space dimension minus the minimum state space dimension plus the minimum leg, it says. Agree? I simply use this one. This Q is L min, this is N min, and it gives me this inequality. But this inequality tells me something interesting. And now, all of a sudden, plus appears. We should forget about plus. This is N, this is L. In the original paper, there are both upper and lower bounds, and I forgot to delete these pluses. I'm going to do it after the lecture. And this is capital N, basically. But it says that I can find an upper bound on the leg from the data, because N, capital N, is the highest the bound on the state space dimension. So if I take N here, the highest leg I have has to be less than or equal to this, right? So from the data, I get LD, a new bound. I have already a bound, L, so I can take the minimum of them, which I denote by LA. All these things are on the base, I can find from the data. I find delta integers, I find Q, and then it gives me L min and min, and then this is also based on data. LA, I can figure it out. Okay? And that is the actual bound. LD is the bound determined by the data. Okay? Now, here are the necessary and sufficient conditions. The data are informative for system identification if and only if T is greater than or equal to this number, and rank of the Hankel matrix, input-output Hankel matrix, at depth LA plus 1 is equal to this number. Okay? Moreover, if these conditions are satisfied, then L true is L min, N true is N min, and any N min explaining system is actually isomorphic to the true system. So what does it say? It says start from the data, find LA, N min, L min, check this condition. If it is satisfied, you can use the state construction to construct a system, and that is similar to the true system. Okay. there are a couple of interesting remarks. But first, I'm going to mention some special cases. If only L is known, but N is unknown, then I can take, since the system is observable, then I can take N to be PL, that is an upper bound on the state space dimension. And then LA would be equal to L. If N is known, but L is unknown, I can take L to be N. Then LA would be always equal to LD. And still, I can apply the same theorem. What is very interesting, very striking about this theorem, I mean, apart from the fact that it gives necessary and sufficient conditions, is the fact that the condition that needs to be checked depends on the data. Because this LA depends on the data. Huh? And this brings us to our initial discussions. We felt like it's a difficult problem because we knew that it is going to be a rank condition on a Hankel matrix, but we didn't know at what depth we have to check. And at a certain point, we had the feeling that it may depend on the system, therefore you cannot easily characterize. But it turns out that it doesn't depend on the system, but it does depend on the data. Okay? I'm almost finished, as you see. And now, let's compare it to fundamental lemma. So, look at the minimum number of samples this is the fundamental lemma requires, and this requires. This LA is going to be always less than or equal to L. It cannot exceed L. There is this capital N term here, capital N term here, capital N doesn't appear here, and N min is definitely less than or equal to capital N. So it makes quite some improvement on the data efficiency. Maybe if you look at an example, that's going to be, if you look at examples, it's going to be easier to see. Here is a system with 2 inputs, 2 outputs, leg 2, 3 states, and then we collect this data. Okay, and then we find these delta integers, L min. These can be done all on the basis of the data. Now, if I take these bounds, upper bounds, then the data I started with gives me this LD, this LA, and I apply the theorem. And all these ticked cases, the theorem says you can identify the system. But in none of these cases, fundamental lemma says I can identify the system. Because, for instance, when the upper bounds are both 4, fundamental lemma requires at least 26 points, whereas I have almost half of it, 14. And if the size of the system grows, then the difference, the gap between what fundamental lemma requires and what our result requires gets bigger. Here is, well, I don't have that example, but you have, you are going to show it. So the coffee is out there, I hear it. Basically, in the first part, what I did is to prove this theorem. Where is it? This theorem. Okay? It gives me necessary and sufficient conditions for informativity for system identification. Okay? But it tells me also something. Maybe I should connect it to your talk at this point. It tells me that the right-hand side is the minimum number of samples one needs. And I mean, it should be not, sorry, it's not the minimum of number of samples, but it says you cannot identify the system if you don't have that many samples. But the problem is, of course, this n min is going to be, if these conditions are satisfied, it's going to be n true, which is something I don't know. So I do not know this number up front. So there are two questions then. A, can I devise an online experiment? And B, can I achieve the minimum here? But it is a very weird problem because I do not know this number. Is it possible to devise an experiment even though I do not know this number up front? Some miracle happens, and the experiment tells me, okay, this is the number you didn't know up front. And that is what Hank is going to present. Any questions? Yes? Yeah. Since you know behaviors, it's going to be easy. I had a few slides, but I mean, it's already too technical. I skipped them. So if you take a row-reduced kernel representation, these deltas tell you the number of a delta k tells you how many lows you have with power k. I can, you know behaviors, right? I mean, if you study anything with Madhu, of course, it's, so you can, there's a one-to-one correspondence between submodules of polynomials and behaviors. If you have a submodule, you can find a certain basis, the minimal basis with the least possible degrees of the rows. And these deltas give you how many rows with certain degree you have. There is a very good meaning of these deltas. Any other questions? Let's have coffee then.